Ever wondered how databases maintain their integrity and consistency? It's all about the rules, or as we call them in the database world, structural constraints. Just like the pillars of a building, these constraints provide a solid foundation for the data in a database, ensuring its accuracy, consistency, and reliability. Imagine them as invisible hands, guiding the data, ensuring it adheres to defined rules and preventing any anomalies. These are not mere guidelines but enforceable rules that are implemented using mechanisms like database triggers, rules, or constraints defined at the schema level. They are the unsung heroes, working behind the scenes, making sure that every piece of data fits perfectly like a puzzle piece, maintaining the overall picture of data integrity. So what are these structural constraints? How do they function? And why are they so crucial in database systems? Now let's dive into the different types of structural constraints and how they work. First up, we have the primary key constraint, the unique identifier of each record. Imagine you're a librarian and you're trying to organize the books in your library. It would be a chaotic mess if every book didn't have a unique identification number. This is where the primary key constraint comes into play in the world of databases. Just like every book in a library has a unique identification number, every record in a database table has a unique identifier called the primary key. This key is the backbone of the table. It's what makes each record unique and distinguishable from every other record in the table. It's a rule that says, hey, no two records can have the same primary key. Now let's take an example of a student database. Each student is assigned a unique student ID. This student ID is the primary key of the student table. It's unique for each student and helps us identify a student record in the database. Whether it's John, Amy, or Zara, each of them will have a unique student ID. And here's the deal. It's not just about being unique. The primary key constraint also insists on not accepting null values. That means every record must have a primary key. So in our student database, there can't be a student without a student ID. It's non-negotiable. The beauty of the primary key constraint is not just in maintaining uniqueness, but also in its role in establishing relationships with other tables. It acts as a link to connect records between tables, like a bridge connecting two islands. But more on that when we dive into the foreign key constraint. So, in short, the primary key constraint is a rule that ensures each record in a table is uniquely identifiable. It is the cornerstone of data integrity and organization in databases. Without it, we'd be lost in a sea of data, unable to tell one record from another. That's the primary key constraint, ensuring each record is unique and identifiable. Next, we have the foreign key constraint, the link between tables. Now, what does this mean? In essence, a foreign key constraint establishes a relationship or a link between two tables. It's a way of maintaining referential integrity within your database. Imagine you're a college administrator. You have a table for students and a table for courses. Each student can enroll in multiple courses, and each course can have multiple students. So how do we link these two tables together? That's where our friend, the foreign key constraint, comes into play. On one hand, we have the students table, with each student having a unique student ID. On the other hand, we have the courses table, with each course having a unique course ID. Now we create a third table, say enrollments, which captures the relationship between students and courses. In the enrollments table, we have a student ID column and a course ID column. These columns are foreign keys, referencing the student ID in the students table and the course ID in the courses table respectively. This connection between tables is the essence of the foreign key constraint. It ensures that you can't enroll a student in a course that doesn't exist, because the course ID in the enrollments table must correspond to a valid course ID in the courses table. Similarly, you can't assign a course to a student who doesn't exist, because the student ID in the enrollments table must correspond to a valid student ID in the students table. In this way, the foreign key constraint safeguards the integrity of your data. It prevents you from making mistakes like enrolling non-existent students in non-existent courses. It's like a vigilant guardian, ensuring that every piece of data in your database makes sense and follows the rules. But remember, the foreign key constraint doesn't just restrict you. It also empowers you, enabling you to establish and explore complex relationships between different sets of data. So that's the foreign key constraint, the glue that holds related data together. Moving on, let's look at unique, check, and default constraints. These are 3 more structural constraints that help maintain the integrity of our data. First up, we have the unique constraint. This ensures that the values in one or more columns of a table are unique. For instance, when a user signs up on a website, their email address must be unique. The system can't have 2 users with the same email address, right? That's where the unique constraint comes in handy. It ensures that no duplicate email addresses are entered into the database. And unlike a primary key constraint, a unique constraint allows null values. Next, we have the check constraint. The check constraint enforces specific conditions on the values allowed in one or more columns of a table. Say, for example, you're running a website that sells alcohol. You need to ensure that no one under the age of 21 can purchase alcohol. Here's where the check constraint shines. It ensures that the age field for each user is 21 or above, thereby enforcing the legal drinking age. Lastly, we have the default constraint. The default constraint specifies a default value for a column when no value is explicitly provided during an insert operation. Think of a scenario where a new user signs up on your website but doesn't specify their country. In such a case, you can set a default constraint to assign a default country like United States or United Kingdom. This way, there's always a value in the country column for every user. So, to sum it up, unique constraints ensure there are no duplicate values. Check constraints enforce specific conditions, and default constraints set default values when none are provided. These constraints play a vital role in maintaining data consistency, preventing data anomalies, and ensuring that our databases are reliable and accurate. These constraints help us maintain data consistency and prevent data anomalies. Finally, we have the entity integrity constraint, a rule that ensures each row in a table is unique and identifiable. It's like the gatekeeper of our database castle, making sure that no 2 rows are identical, and each has its own identity. This is crucial in maintaining the overall integrity and reliability of our data. To illustrate, let's imagine a table that stores information about books in a library. Each book is assigned a unique identification number or ISBN, which serves as the primary key. The entity integrity constraint ensures that every book or row in the table has a unique ISBN and that no ISBN is null. This means that each book can be uniquely identified by its ISBN, and there are no books without an ISBN. But what happens if we try to add a new book without an ISBN or with an ISBN that already exists in the table? Well, the entity integrity constraint steps in. It prohibits the addition of a new book without an ISBN or with a duplicate ISBN, thereby ensuring that every book in the library is uniquely identifiable and that no 2 books share the same ISBN. This is the beauty of the entity integrity constraint. It works quietly in the background, maintaining the order and consistency of our data, and while it might seem like a small detail, it has a significant impact on the overall integrity of our database. By ensuring that each row in the table is unique and identifiable, it prevents data anomalies and maintains the reliability of our data. And there you have it. The entity integrity constraint, the unsung hero of our database system, working tirelessly to maintain the integrity, consistency, and reliability of our data. It's a testament to the power of structural constraints in database systems, and a critical component in ensuring the accuracy and usability of our stored data. Entity integrity constraint ensures that each row in a table is unique and identifiable, contributing to the overall integrity of the database. So, we've unpacked the various structural constraints, but why are they so important? Well, it's simple. These constraints play a pivotal role in maintaining the integrity of our databases. They act as gatekeepers, ensuring that all data entering the database meets certain criteria and adheres to predefined rules. Remember the primary key and foreign key constraints? They're there to ensure that each record in a table is uniquely identifiable and that relationships between tables are maintained. Then, there's the unique constraint, which guarantees uniqueness across all rows for specified columns. Not forgetting the check and default constraints. They respectively enforce specific conditions on values and provide default values when no explicit input is given. Lastly, the entity integrity constraint, which ensures that every row in a table is uniquely identifiable and no primary key attribute contains a null value. And there we have it, the role of structural constraints in maintaining the integrity and consistency of databases, ensuring the accuracy and usability of the stored data.